Welcome back class to our course on mechanical behavior of materials part 2. So in the last class we discussed about fracture toughness measurement using ASTM E399. Okay. So we have already completed the part I wanted to talk about fracture mechanics, and we have mostly dealt with LEFM, linear elastic fracture mechanics. I already mentioned that the concept related to EPFM is not part of this course, so we are not going to talk about that. Okay? So today we will start talking about fracture mechanisms in metals and alloys, and eventually in this course we will talk a little bit about ceramics as well as composite materials also. Okay, so let's begin mechanisms. Okay, so what are the mechanisms for failure? So we'll start using the concept of uniaxial tensile testing, which you are already familiar. Okay. So if I have these two plots, so say you have S and E, where S is engineering stress and E is engineering strain. And if one of the plot is this and another plot is something like this, not up to the scale, okay, but the nature is like this. So not up to the scale, but the nature is like this. So this one is brittle material and the other one is ductile material. Okay. So these two things you already know. We have discussed this in the previous course, mechanical behavior of materials part 1. So let's go into more depth of failure in these type of materials and how the fracture surfaces are going to look like. So type of failure in uniaxial tensile test. So what are the different types of failures we can have? So the first one is so basically what you are doing, you have a specimen, right? Say dot bone specimen. Okay, and then you are pulling it. So that is what uniaxial tension is about, right? So what I am drawing here is the part of dot bone specimen, that is the dead section where we are about to see the fracture, right? You know that typically, not typically, it has to be in the dead section, right? During tensile test. So if your failure occurs like this, like flat, so it is the failure is occurring along a plane. We call it cleavage plane. And if this is the case, we have brittle. Okay, so the material is brittle. Now the second case can be something like this. Remember, this is the this session we are talking about. So these are under uniaxial tension. And these planes where you are going to see a slip, these are slip planes. Okay. this is a typical case of Sayre. Okay. So this is second case. Now the third one is something like this. Okay. So you have necking, and then the failure occurs at a point. This is called rupture. Okay. So failure is occurring at a point after necking. And the last one, which I think you already know, is something like this. So you have necking during tensile testing. And then you see a typical cup and cone failure. Something like this. Okay. So this is a typical case of cup and cone fracture. Okay. So the two sides are there when you do tensile testing. So one side will look like as a cup, and another side will look as it is a cone. Okay. So in this case, if I see it, so this is like cup, and this surface here is like a cone. Okay. So we call it as cup and cone fracture. Now, in which case you are going to observe these features, or not these features, these phenomena. Okay. And remember that all these three are related to ductile failure. Okay. So now when we talk about cleavage failure in brittle material, here you are not going to see any deformation, or even if the deformation is there, it is very little. So little or no deformation. And this can happen in single as well as polycrystalline. Okay. Now let's talk about the shear. So here you are going to see shear fracture of ductile single crystal. Okay. So first of all, it is a ductile failure, and it will happen when you have a single crystalline material. Okay, so if you have a single crystal, some planes are more favorable towards deformation. Right? Remember the Smith criteria. Okay, so on those planes, you're going to have slip occurring. Okay, and that will lead to the shear. So shear fracture of ductile single crystal. The third one, which is the rupture, where the failure is occurring at a point after necking has occurred. This will also occur in ductile material, but it is of pure nature. Okay. So completely ductile fracture of polycrystalline. Okay, and this is for pure metal. Now the last one, cup and cone fracture. This is also a ductile failure. Okay. And for mostly polycrystalline. Okay. So these are, and we call it also for commercial alloys. You can see that. So if it is pure metal, you are going to see rupture. If it is in commercial alloys where you have presence of second phase particles, second phases, I am going to discuss about that. Then you are going to see cup and cone fracture. So we are going to eventually discuss the mechanism of formation of cup and cone in a polycrystalline commercial alloy. Okay, we'll do that eventually. So this is the type of failure you observe when you do tensile testing. So there another way of classification of fracture, and this is from Dieter. So fracture can be classified based on the four characteristics. Okay, so the first is crystallography mode. Second is appearance of fracture surfaces. Third is strain to fracture or strain to failure. And the last one is crack path. What is the path of crack propagation? Okay. So these are the four ways a fracture can be classified. So let me make a table so that you can understand how we are defining the different class of fracture using these four criteria. So first is, let's say, behavior. Okay. Then the terms we are using. So crystallographic mode. So shear, and then we know if it is shear, it is ductile behavior. Okay. And if it is cleavage, then it is brittle. We just saw this, right? So if you have a shear, then it is ductile type. If it is cleavage, then it is brittle type. So that is what I mean by crystallographic mode. Okay. Now the second one is appearance of fracture surface. So it can be fibrous or it can be granular bright. So if your fracture surface is fibrous, dull nature, then we typically say energy has been absorbed. So it is ductile nature. If it is granular and bright, then we say it is brittle nature. Okay, so that is how we define when we look at the fracture surface. Okay. Third is strain to fracture or strain to failure. So if you remember, I drew stress strain plot, and you know that if strain to failure is small, right, then it will typically lead to the brittle one, and if it is very, very large, it will typically lead to the ductile one. That is the characteristic, if you remember this particular plot here, right? So same thing. So that is what I mean by strain to failure. So if it is ductile, then large amount of plastic deformation. And if it is brittle, very little or no plastic deformation. Okay, so that is what I mean when I say strain to failure for classification of fracture. And the last one is crack path. So you already have generated a crack. Now how this crack is propagating under applied stress. So that will determine the classification of fracture. So in this case, we have either transgranular or intergranular. So here when we talk about the transgranular crack path, that means crack is propagating through inside the grain. Okay. So crack propagates through grains. So this is transgranular, or sometimes we call it as intragranular. Okay. Now the other one is intergranular. So here crack is propagating through grain boundaries. So crack propagates through grain boundaries. Okay. So this is how we can classify the fracture. And this is I have taken from book of detail. So now let me make a schematic so that you can understand better what do I mean by transgranular, intergranular, etc. So you can have different, and again remember, we are talking about uniaxial tensile test now. Okay. So you have two conditions. Something like this. Okay. So you are under uniaxial tension. And then these two are polycrystalline materials. So you are going to have different grains, right? So in the first one, the crack is propagating through the grains, okay, inside the grains. Okay, so you have these three grains here. So crack is propagating through these grains. Okay, so this is transgranular. In the second one, it is propagating through the grain boundary. Okay, so these are your grains here. Something like this. Okay, so these are your Grains here I am marking in purple. So these are your separate grains. And the black lines are your grain boundaries. Okay. So you have a track which is propagating through the grain boundary. So this is intergranular. And both are brittle. Okay. You're not seeing any necking here. If you see, the fracture is has occurred without necking. You see, there is no necking in this region. So very less plaster deformation. And if it occurs through the grains, then we call it transgranular. If it is occurring through the grain boundary, we call it intergranular. Okay. Now, when you see a necking happening or a shear, if it is a single crystal, then it is a ductile one, right? So now let's talk about that part. So in ductile also you can have transgranular, intergranular, etc. Okay. So now I'm going to have some necking here. So let me draw 4 like this. Again, these are schematic. Okay. So I've made 4 schematics here. Now let me draw grains. So the blue lines are your grains. Okay. So if it is transgranular, then you are going to see cracking. Okay. Inside the grains like this. So you are seeing some voids. We will see why voids are going to form in ductile failure. Okay. So just for now, just see that they are forming voids, and these voids are inside the grains also. So this is a typical case of transgranular. Here, the voids are forming in case 2 along the grain boundaries. So this is a typical case of intergranular. Okay. And these are related to plastic growth of voids. Again, we will discuss why voids are forming and where it should form when we talk about ductile failure. Here you are seeing rupture, right? So here you just see necking at a point. And the last one is shear localization. So shearing along a plane, right? And all these are related to ductile behavior, ductile fracture. Okay. So again, remember in the first case, you are not seeing, in the brittle one, you're not seeing necking. So very less plaster deformation. But you have both transgranular and intergranular. In the second case, it's all ductile. You see necking, whether it is pure element or pure metal or commercial alloys. Okay. And the last one is shear localization, where the localization is occurring along the slip. So all these are ductile failure. Okay, so now let's talk about uh, the different kind of fracture mechanisms, right? The important ones, and then we'll discuss them. Okay. So the first one is your ductile fracture. Second one is brittle or brittle cleavage fracture. And third one is intergranular fracture. See, when I say brittle failure, it can be cleavage, it can be intergranular also. Okay, so cleavage is completely different, although it will be part of brittle one. Okay, so these are the three dominant fracture micromechanisms in metals and alloys. So we'll focus on first and second. Okay, so we'll talk about first the ductile fracture. So we'll talk about ductile failure first. Okay, so now use again the tensile loading, uniaxial tensile testing, and see how we understand the fracture mechanisms. Okay. Ductile fracture. So as soon as materials reach an instability point, I hope you remember what is this point during uniaxial tensile loading. So that is the maximum point, right? Instability criteria. We have discussed this in our course 1. So here what you observe is that strain hardening is less than the reduction in load. And that's why the curve goes down. Okay. Okay. So the increment in the load you are getting from strain hardening, that effect is less than the decrease in the load because of the reduction in cross-sectional area, right? So you are getting that when you are in the instability point, and that's why the curve goes down in engineering stress, engineering strain plot. Okay. Reduction in here, sorry, it should be area. Okay. Now we can have two cases. One is pure metal and another one is commercial metals and alloys. And there are some characteristics when we have pure metal and commercial metals and alloys and we do tensile testing. We have discussed that already. So pure metal is going to show what type of failure? Rupture, right? At a point it is going to fail, whereas commercial metal and alloys, they are going to show cup and cone failure. Okay. So here it can neck down, the specimen can neck down to a single point. Okay. And you're going to have very large local strain, because as soon as necking happens, you are doing tensile testing, right? So all the strains are going to be localized in the net region. And remember, this is rupture, right? So you are going to come to a point. That means you are going to have very large strain in the net region, right? So very large local strain. And the third characteristic is it can go to nearly 100% reduction in area. Whereas when we have commercial metals and alloys, you are going to see cup and cone failure. It is going to fail at a slightly lower strain, not slightly, it is going to fail at a lower strain as compared to pure metal. Okay, and this happens because of the void nucleation at inclusions or second phase particles. So if you have pure metal, right, you are not going to have second phase particles or inclusions. I will show you one or two images of what do I mean by inclusions and second phase particles, especially in aluminum alloy. I am going to show you in the next class. So when you have pure metal, you're not going to have these inclusions and second phase particles. So you are going to observe rupture. Okay, it will fail at the single point. But in commercial metals and alloys, because these are commercial alloys, you are going to have inclusions or second phase particles in the matrix, from where, due to the strain localization, voids are going to nucleate. Okay, and as soon as that happens, you can foresee, right, that the strain is going to be lower than what we are going to observe in pure metal. We are going to discuss in detail about that also. Okay. So now let me plot stress strain curves for both pure metal and commercial metals and alloys, and then show you the comparison with respect to the necking characteristic. So S, which is engineering stress, and E, engineering strain. So we have two plots. So say one is so this is for pure metal. Again, not up to the scale. Typically, the elastic regime is much smaller than the plastic regime. Okay, but just for understanding, I'm drawing like that. So this is the case of pure metal. Okay, and if I have commercial alloys or metal, it will show something like this. So it is going to fail much earlier. Okay, so this is the case of commercial metals and alloys. Okay, so if I denote this as point B, this as point C, and then here you have point A. Okay, so at A, about at A, you are going to have necking. Okay, and I am assuming here that necking is taking place in both the cases at the same location, just for understanding. Okay, so now at point B, how your sample is going to look like, and remember you are doing this tensile loading, right? Tensile testing. So so we have a dot bone sample. and then you are having load here. Okay, and we always talk about this particular region, right? So at point B, you are going to have a condition like this. Something like this. Okay, so this one is your cup, this one is your cone. Okay, two parts of your sample, and at point C dash, which corresponds to pure metal, you are going to see rupture. Okay, now at point A, and I am assuming that both the materials here, commercial metals and alloys and pure metal, the necking take place as A at A point A. Okay, so the necking is occurring at point A. So your sample is going to look something like this. Right? And this is your neck here. Okay, so at point A, both the samples are going to have this phenomena or this characteristic. Now, for commercial metals and alloys after fracture, you are going to observe, see I have given on the left side, cup and cone failure, whereas for pure metal, you are going to observe point C, which is rupture. Okay, so the strain is going to be higher for pure metal as compared to commercial metals and alloys. Okay, because point A remains same, and at point B you can see the cross section area is much larger than what is observed in the case of rupture. So obviously the strain to failure is higher in the case of pure metal. Okay, and this is happening, I mentioned, because of the presence of second phase particles or inclusions in the case of commercial metals and alloys. So overall, ductility in commercial metals and alloys will depend upon the presence of these second phase particles or inclusions, their size, morphology, and distribution. Okay, so ductility in commercial metals and alloys is limited by volume fraction, size, and distribution of second phase particles or inclusions. Okay, so I will stop here and we are going to discuss about the tile fracture mechanisms further in the next lecture. Thank you.